All right, so 6.3 is honestly something that's not all that connected to the first two lessons that we've done in this chapter so far, but something that you have done before is you guys have simplified square root expressions. So we should be familiar with square root expressions. Remember, the general idea when you're taking a square root is that you're trying to figure out what multiplies by itself in order to give you that number. And so we've been dealing with some that come out perfectly even. We've been dealing with some that we can just simplify. So instead of dealing with square root expressions, which like I've said we've seen in past chapters, we are going to be looking at square root functions. We're going to be graphing them, analyzing them, and then also taking a look at inequalities at the end of the section. So square root function, very simple definition. It's just a function that contains the square root of a variable. Function that contains the square root of a variable. So basically, I mean, it's exactly as it sounds. A square root function is a function that has a square root, and then there are going to be variables involved somewhere. So the parent function of a square root function. We have done the parent function of the absolute value, and we've done the parent function of the parabola. So the parent function means like the original, before you make any transformations, before you, stretch it, or reflect it, or move it left or right, or up or down. So the parent function is just the simplest function. It's like this: f of x equals the square root of x. All right, and so I'm just going to give you a picture of what it looks like over here on the side, and then we're going to analyze exactly what all of these pieces mean. So square root, you can plug in certain x values. So say you take the square root of 0. Square root of 0 is 0. So we've got our first point right here. And then like the square root of 1 is 1. The square root of 2 is not something that comes out evenly. The square root of 3 is not something that comes out evenly. Square root of 4 is 2, so we've got our next point that we can plot right there. And then the next point we'd be able to plot is the square root of 9, which is 3. Then the square root of 16, which is 4. So this function is curved, and it's increasing very, very slowly. Whoops, pretend I went through that point. All right, so the square root function looks like that. Now over on the left, I'm not allowed to plug in like a -1 or a -2. Those wouldn't give me real answers. They'd give me imaginary answers, and I can't plot imaginary answers on a graph. So domain, remember, is all of the x values that you're allowed to plug in. So far, our domains have been all reals, and I told you that there will be a time where the domain won't be all reals. Well, we have reached that time right now. So the domain is only numbers that are greater than or equal to 0. Okay, you're not allowed to plug in a -1. You're not allowed to plug in a -2. But you can take the square root of 0 or anything above it. All right, and then the range, remember, is the y values that you get out. This is the very lowest y value right here. Notice there's nothing below it down here anywhere. So same range as the domain. This time y has to be greater than or equal to 0. I guess not has to be. That's the way it comes out when you plug in different values. Intercepts. Intercepts, where is our x-intercept? AKA, when does the function hit the x-axis? That would be right here. So our x-intercept is 0. And then where does our function hit the y-axis? And that would also be right here. So our y-intercept is also 0. Okay? When is the function not defined? Not defined meaning we're not allowed to plug in the certain values of x. Function is not defined when x is less than 0. Again, we can't take square roots of negative numbers. All right, and then the end behavior, last thing is, so this end behavior is the weird, it's like the approaching thing. So as x approaches 0, meaning if we're looking this way on the graph, as x gets closer and closer to 0, y is approaching 0 as well. So our function is approaching 0. So the closer the x value gets to 0, meaning as I kind of head off to the left here, my function value is approaching 0 because I hit the origin right here. So as x goes to 0, f of x goes to 0. And then as x goes to infinity, oops, that was not a good infinity sign, meaning as I go off to the right here, very, very slowly, it just climbs and climbs and climbs and climbs. So technically, the function just keeps going up and up, meaning the function will also approach infinity. All right, so end behavior, don't let that freak you out too much. Basically, this means that my graph stops 0, 0. That's what this first line means. And the second line means as I go off to the right, the function's just going to keep going up and up and up. All right, so we're going to look at some, other page. We're going to look at some domain and range questions. All All right, so now these ones are different. These are no longer just the parent function. They are transformations of the original function. So I'm trying to find the domain and range. Start with the domain. The domain is anything that makes the inside greater than or equal to 0. Okay, so only non-negative values inside. So we need this x minus 3, whatever is inside the square root, we need this to come out to be greater than or equal to 0. Because the stuff underneath the square root, we need it to be positive for sure. All right, so I just add 3 to both sides. And that's all I need to do. So x has to be greater than or equal to 3. All right, and I can plug in anything beyond that. And then in terms of the range for my y values, there's nothing here that would make my graph move up or down or would change from my normal range. So if I plug in like 3, the square root of 0 would be 0. Then if I plug in 4, I'd get the square root of 1, which is 1. So the lowest possible y value that I can get is still 0. So that's my domain and range. So x can be anything greater than or equal to 3. For example, if I tried to plug in a 2, 2 minus 3 would be negative, and I can't use a negative value. And then my range is y is greater than or equal to 0. Okay? Next one right here. So this one's a little different as well. I have something different underneath the square root, but then I also have something different outside the square root. Okay, so here's how this is going to work. I need to take still this piece and make sure that it ends up positive, because the stuff underneath the square root, the radicand, we talked about that a while ago, the stuff underneath the square root can't be negative. So I have to set up a little equation like this. Then I can subtract 6 from both sides. So as long as I pick an x value that's greater than or equal to negative 6, I'm good to go. I can plug in anything that's beyond that value. If I tried to plug in something smaller than that, I would end up with a negative under the square root, and that would be undefined. Okay? Really quick way to figure out what the range is you just plug in this lower limit. Like here, if I plugged in the 3, I would have 3 minus 3, which is 0, and the square root of 0 is 0. So that always gives you your lowest possible value. If you pick the first x value that you're allowed to plug in and plug it in, then you get the lowest possible y value. So I'm going to do the same thing right here. So again, we're finding the function value at negative 6 in order to determine the lower limit of the range, kind of like we did here. So f of negative 6, if I plug that in, I have the square root of negative 6 plus 6, and then plus 2. So this plus 2 on the outside is going to come into effect here, because this is 0. Negative 6 plus 6 is 0. Square root of 0 is 0. This tells me that my lowest possible value is 2. So even if I plug in the lowest x value that I can, when I have this plus 2 on the outside, it brings it up. So the lower limit of the range is 2. But it can be anything greater than or equal to that value. Okay, so keeping these ideas in mind is going to help us to graph these square root functions, which is the next thing that we're going to be looking at. And we're going to write down what these transformations mean. So if you look here, this is my kind of generic square root function. You can see I could have something underneath the square root, which I dealt with twice, here and here. I could have something outside the square root, which I dealt with right here. I could even have a number in front of the square root. All right, so these values, the a, h, and k, you might notice that this looks pretty similar to vertex form. And so the same things can happen. We can have horizontal translations, vertical translations, and then orientation means the way it's facing, like if it's flipped or whatever, and shape. So h is a horizontal translation, so that is based on the value of h, whatever you've got in here. So you move, now this is, remember, the opposite of what you think it should be. So if you have like an x minus h, for instance, if it's x minus h, what you end up doing is you move h units to the right. Remember the way it works when it's inside a function with the x? Remember we talked about how x lies? So it is the opposite of what you think it's going to do. So if there's a minus, you actually move to the right, even though it's kind of counterintuitive because x lies. If you have an x plus h, like we did right here, it actually moves that many units to the left, which is exactly what this one did. It moved 6 units to the left, and it started at negative 6 instead of at positive 6. And this one moved 3 units to the right, and it started at positive 3 instead of 0. So this means you move h units to the left. So just always remember that x lies. Whatever there is right there with the x, that's what you're going to end up getting. And then the domain is always x is greater than or equal to whatever the h is. Okay? So domain, we always get x is greater than or equal to h. All right, our vertical translation. Vertical translation has to do with k. That's the number on the outside. Now the number on the outside does exactly what you think it's going to do. Okay, so if you've got a plus k on the outside, then you're going to move k units up. Whereas if you have minus k on the outside, you're going to move that many units down. Okay, so y doesn't lie. So if you've got something on the outside like this, it does move up or down exactly like you think it would. So this one, if you have a plus 2 on the outside, my range moved up 2 units. Okay, so my range, it depends on what my shape is, whether my graph is right side up or upside down. So I'm going to come back here to write the range in just a second. Okay, so now orientation and shape has to do with A, the letter that you've got in front right here. So 2 things. First of all, if the A is negative, okay, so let's say if A is negative, that flips the graph upside down. Same way it did with the parabola, same way it did with the absolute value function. If A is less than 0, the graph gets flipped upside down. And then we could also have some sort of stretch. So if we're going to say the absolute value of A is greater than 1, because it could be like a positive 2 or a negative 2. So if you've got a value bigger than 1 in front of the function, then it gets stretched vertically. And then if your value of A is somewhere between 0 and 1, like a fraction, then that's a vertical compression. And we've been dealing with these transformations with every type of function that we've looked at. Okay, so now back up here for the range. If we're talking about the range, now we've got one of 2 things. Like let's say A is greater than 0. Like my graph isn't flipped upside down. If my graph isn't flipped upside down, then the range is just y is greater than or equal to k, just like it was here. Since I had a 2 out front, it was just y is greater than or equal to 2. If your graph gets flipped upside down, then that actually becomes the largest value rather than the smallest value because you get flipped upside down, similar to a parabola. Then you can be anything below that value instead. But once we see an example, I think this will be a little bit more clear. Okay, so these are some of the transformations that we can make. This example, we're going to graph the function, state the domain and range. All right, so graphing the function, we want to look at what we've got going on the outside. We want to see what we've got going on the inside. So start with this 2. What the 2 is going to do is it's going to be a vertical stretch. All right, so first thing we're going to have is a vertical stretch by a factor of 2. So depending on how big that number is, that tells you how big the stretch is going to be. A stretch of 3 would be bigger than a stretch of 2. A stretch of 1.5 would be smaller than a stretch of 2. So I'll show you exactly what that looks like. Okay, and then the number on the inside here, the plus 4, means I move 4 units to the left. It's always counterintuitive with x because x lies. And then I don't move up and down. Okay, so no movement up or down because there's no number out here after the function. So say no shift up or down. Okay, so let's graph what that function looks like. All right, so I'm going to fill a little spot over here. So I'm going to move 4 units left. 1, 2, 3, 4. No shift up or down, which means my graph is going to start right here. Now, my square root function typically looks something like this, like the parent function that I graphed. We already moved it over to the left like it's supposed to be. But a vertical stretch, remember a stretch means your graph is getting pulled in this direction. So if this graph is getting pulled in this direction, it's going to be taller. All right, so rather than being so short like this one, it's getting stretched, so it's going to be taller. The bigger the number, the bigger the stretch. All right, so we are looking for just a very, very brief sketch here. We need to know where this point is, but other than that, so a stretch of 2 means it's getting pulled up a little bit higher than the original function would be. All right, make sure you've got the right shape down, make sure you know where the graph starts, but other than that, it's a pretty general sketch. Okay, let's look at another one here. All right, so this one, the 1/4 out front, tells you that you are being vertically compressed by a factor of 1/4. So it's almost like your graph is a quarter of the height as it once was. So it's going to get squashed from the top down. Okay, this number in here, this minus 5, remember x lies, so this is 5 units to the right. Always counterintuitive with those x values. And then the plus 3 on the outside means you're going 3 units up. Okay, now set up your graph for what we've got here. 5 units to the right means we're going 1, 2, 3, 4, 5, and then 3 units up. 1, 2, 3. So our graph starts right here. There's always that starting point where there's nothing to the left of the graph at all. And then it's vertically compressed. So if you were to compare it to the original absolute value graph, it's going to be like a squashed down version. So maybe something like that. All right, so not very tall at all. I missed on the previous one. I need to flip back to this. We were asked for the domain and range. So domain and range for this one, x starts right here at 5. So x, you can plug in anything greater than or equal to 5. And then for y, the lowest value is 3. And the y values will be anything greater than or equal to 3. It's actually pretty easy to figure out once you've got a graph in front of you. So let's go back and do that previous one. All right, so here, furthest x value is -4, so x can be anything greater than or equal to a -4, and then y starts here at 0. The lowest y value is 0. So anything greater than or equal to 0 is my domain. Oops, there we go. Okay, so let's flip on to the next page. We've got some inequalities to take a look at. All right, so if we look right here, guitar's pitch or frequency depends on string length and string tension. The frequency of vibrations is determined by this function right here, where f is the number of vibrations and t is the tension. Okay, so we're going to graph the function and then determine some of these values right here. Okay, so 200 times the square root of t, you get some values, or you get this vertical stretch out front that makes it very, very tall. All right, so if we were to graph just a very general sketch, like 1, I mean, it still goes at 0, 0. 1 is normally at 1, but this time it gets stretched to 200. 1, 2, 3. Okay, so the square root of 4 is normally 2, but it's going to get stretched up to 400. All right, so that'll give us just a very general idea of what this graph is supposed to look like. Something like that, a stretch of 200, which we need to mark on the axis here. And then determine the frequency for 3, 6, and 9. So if I plug in different values of t, my function is 200 root t, and we're actually going to use a calculator for this. So if I try 3, 6, and 9, I'm plugging it into this function. It's like 200 times the square root of 3, and I'll get a decimal approximation for that. 200 root 6, I'll get a decimal approximation for that. And then 200 root 9, I don't need a decimal approximation because the square root of 9 is 3. So this is actually just 200 times 3, which is 600. But for the other two, I'll get a decimal approximation, and I will show you what that will look like. Okay, so we've got 200 times the square root of 3. That gives you about 346.41. And then we can do 200 times the square root of 6, and that gives you about 489 point, we'll just go 0.9. All right, so just those values, that's all we're looking for. And then we've got these frequency values over here. So just a little story problem. All right, last thing to finish up is these square root inequalities. Very similar to what we just graphed. The definition is just as trivial as the one on the other page. Square root inequality is an inequality involving square roots. All right, so it seems like almost a silly definition to actually write down, but it is the definition. All right, so graphing the following inequalities. So we should know how to graph these functions, and then we can bring in everything we know about inequalities. You know, should the line be solid or dotted? Should I shade below the graph, above the graph? Where should it be? So with this one, we're going to start with, so 2x plus 1. To figure out the domain, we are going to take the 2x plus 1 and set it equal to 0. Okay, so if I subtract 1 from both sides, divide by 2, I get x equals -1/2. Or I guess I should be setting it, I want to know when it's going to be greater than or equal to 0. So I end up with x has to be greater than or equal to 1/2. All right, so just to set this graph up very briefly, so x has to be greater than or equal to -1/2. So if we say that's a -1, My graph starts right there. All right, and then if I plug in the negative 1/2, there's no vertical shift number on the outside here, so it's not going to go up or down. It's just going to start right here and just look like a pretty typical square root function, like that. All right, I just made it a solid line because this is a greater than or equal to. And then the last thing you do is you plug in a test point. So I can use 0, 0, kind of my normal test point here to plug it in. So we're going to do a test just to see if we should be shading towards 0, 0 or away from 0, 0. All right, so 0, 0, if we were to plug that in, is 0 greater than or equal to the square root of 0 plus 1? So is 0 greater than or equal to 1? And no, it's not. That's false. So rather than shading towards where the 0 is, we are going to shade away from where the 0 is. Okay, so anything, and now the trick with these, you've got to be within the domain. So here, you don't put anything on the side of this. Okay, the graph doesn't start here, so there's no shading that happens over on this side. So 0, 0 doesn't get shaded, so you don't shade this way, you shade the other direction. And now it has to be within the domain. You don't even consider what's happening over here because you wouldn't be allowed to plug it in anyways. So you stop where the domain stops and you just shade everything above for this one. Okay, next one, last one. So we want to know this right here, what would make x plus 2 greater than or equal to 0, so we can get our domain. Subtract 2 from both sides, so x has to be greater than or equal to negative 2, and then this minus 4 on the outside means I'm moving down 4 units. All right, so let's set up what we've got so far, at least our starting point. So 1, 2, start at negative 2, and then it moves down 4 units. 2, 3, 4. So this is my starting point right here. Now, important thing with this, there's a negative out front. So we've got our first example with the negative out front. So what it does is it takes the graph and it flips it upside down. So you see the way this one works, kind of curves this way. We're going to flip it upside down and it'll look something like this. Okay, so it's an upside down version of what you've got right here. Okay, now last thing, test 0, 0. Oh, shoot, should have been a dotted line. Dotted, just pretend. See, this is why I let you guys draw me little notes because it's very easy to forget to make it dotted. Okay, so now let's test 0, 0. So test 0, 0 is 0 less than a negative square root of 2 minus 4. Okay, so we don't need to know what this is to know that it's negative. So we want to know, is 0 less than a negative? No, 0 is bigger than negatives. And so we end up, I didn't leave you tons of room here, but we end up shading down below this graph. And if I left more room, we would shade more room down below the graph, but both of them we ended up shading away from 0, 0. All right, so lots of stuff that we're looking at there. The next thing that we'll be able to do is we're going to look at more square root stuff and kind of simplifying down square root expressions.